We'll wait for a few minutes. Let them join. So everybody hear me?
Yes, sir.
Okay. So last class had some technical difficulty. Hopefully this is sorted out today. So before we start, I'll just go through what we did in last class. Okay. So Monday you're coming to school. So okay. So basically this is a conductor, maybe some copper or aluminum. So it will have some resistance, right? So I'll connect this to an external. Obviously, I need something to drive the current. So I'll connect to your cell of some potential difference V. Okay. So the current will leave the positive terminal. So it will flow like this. Okay. So I can assume that there is a charge, positive charge, flowing in this direction Q. I mean, let the charge be Q, which flows in the small amount of time, say delta t. Because I wait for a longer time, say 2 delta t, then the amount of charge going will be twice this Q. Okay. When we take a small time delta t, in that let the charge Q flow from this left end to the right end. Okay. So for this charge to flow, we have to do some work. Basically, this is a potential V. Okay, and this is zero potential. If we take this as reference. Okay. So the work done to move a charge between 2 points is the charge value into the final potential minus the initial potential. So, okay. So this formula you can understand. It's actually done in the second chapter, I think. Yes. Okay, it basically comes from the definition of potential, which is work done to move 1 coulomb from infinity to that point. So the work done to move 2 coulombs will be 2 times that. So this is the work done to move the charge from the initial point to the final point for 1 coulomb. The work done to move 2 coulombs will be 2 times this one. So this will come out to be final potential is this point 0 minus initial potential this left end, which is V. Okay, so this is minus Q into V. So this is the work done with the amount of time delta t. So if we take a work done per unit time, okay, that is divided by the time it takes for this work to be done. That will be minus Q by delta t into V. So the charge Q that flows in time delta t is the current, or I can say current is rate of flow of charge, right? So I divided by the time it takes for that charge to flow. So basically this is current. And work done per unit time is power. So when I get the relation that power is V into I, okay, the negative sign for the time being, we'll figure out that. So basically I get this relation, power equal to V into I. So this is the power, that's the energy is required per unit in 1 second to move the charge Q from left end to the right end. Okay, and who is supplying this power? This power is supplied by the cell. It's basically the chemical energy if it is a electrochemical cell. So this is the relation power dissipated is V into I, and for a resistance, V and I are related as V equal to I into R. That's basically Ohm's law. Ohm's law says V equal to I into R. This is for resistance. So I have this relation for power, which is V into I. So in that, if I eliminate V as I into R, I'll get this relation I square R. And if I eliminate the current by putting current I as V by R, I'll get power as V square by R. Okay. And then I talked about cell. Cell is basically a source of potential difference. To drive a current, I need a potential difference, right? So the potential difference provided by the cell. So this is a cell, and the symbol of the cell is one long dash and one short dash. The long dash is the positive terminal, higher voltage. Okay, so there will be a drop from A to B inside the cell. Okay, outside. So cell is a source of voltage which drives the current. So when I connect this cell to an external resistance, the current will start flowing. And because for the current to flow, there has to be a closed path. If you have a cell like this, current will not flow. But if you connect with an external resistance, there is a path for the current to flow. So this current I can find the value if the value of this resistance is known. Okay, so that current will be what is the current flowing here? So on this, if this potential difference for the cell is B volts, then this point I can take it as B, and this I can take as reference as 0 volts. So this point will be at B because it's connecting wire. There is no drop across the connecting wire because it's an ideal wire in the sense zero resistance. Okay, and this point potentially same as this point, the same 0 volts. So the drop across the resistance is P, drop from left to right. Okay, and the current flowing is I. So using Ohm's law, I get P equal to I into R. From there, I can find the current I as V by I. V is the voltage of the cell which is known, and R is the resistance value which should be known because of the known resistance. So from this, I can get the current value. Okay, so another way to understand why the current is flowing is I said for the current to flow, there has to be a potential difference, right, or potential gradient. Another way to understand is whenever we have a potential gradient, there will be an electric field because electric field and potential are related as gradient of the potential. This is second chapter. Okay, so here if I take the length of the conductor, the variable as L, it is dV by dL, and the negative gradient. Okay, so at this, on the left hand side, the potential is V, on the right hand, it's 0. So there is a change in potential from left to right. This is the gradient of the potential, and this will be a straight line variation because this resistance is a uniform resistance. Okay. So once you have the substantial gradient, that means there is an electric field. Okay, once you have an electric field, a charge will move because force on a charge is Q into E. This first chapter. Okay, so when an electric field is there, there will be a force on the charge, which is Q into E. So that way also we can understand there is a current flow because the electric field is there because there is gradient of potential. So I can say whether the current will flow because of the potential difference. That is same as saying it's flowing because there is an electric field because there is a potential gradient. Once there is a potential difference, there is a potential gradient. So once there is a potential gradient, there will be an electric field which will push the charge. And ideal cell will have low resistance. Okay, bring these two terminals effect. So this is 0 ohms. So since it's 0, I can remove it. So this is an ideal cell. But realistic cell will have a small resistance. Like these two are inside of the cell. When the current flows here, the potential here, it's not exactly V. Okay, so I can relate this. So basically now there are two potential difference I can say. So this is across this ideal cell, and these are the two terminals of the cell which is accessible from the outside. So the terminal across these 2 points VAB and E, which is you can say for ideal cell, this will not be exactly equal. This is actually E minus the drop in this internal resistance. That I can get as V's higher potential, right? So the VAB is drop from here to here. So drop from here to here, that is E, this drop is E. And in a resistance, against the direction of current, there will be a potential rise. Because resistance is a passive element. Okay, if the current is flowing in this direction, then this is a higher potential. And this is a very lower potential. And called 0 or some other potential. So along the direction of current, in a resistor, there will be a potential drop. But here the assumed direction of current is towards left, and going from A to B, I'm going towards right. So actually, from moving from this point to this point, there is a voltage rise. The net drop from A to B, this drop which is E, minus this rise. Because rise means negative drop, right? So the drop from A to B will be E minus IR. It's minus. Okay. So if E is 3 volts, okay, and this drop in a good cell will be say around 0.1 volts. So the actual voltage which is available across the terminals of a real cell is 2.9 volts. Okay, it's not exactly 2 volts. So there will be a small difference because it's not a, there is a small internal resistance. 2.9, which is not 3 volts. If it is ideal cell means it will be 3 volts. It's a good cell means it will be 2.9 volts. It's not a good cell means it will be 2.5. Okay. So this internal resistance should be as small as possible. The voltage drop that's available across the terminals is E minus I into R. So it is slightly less than the ideal cell voltage, which is E. Okay. So when you connect this real cell across this external resistance, so this actually, there is an internal resistance R inside, so I have to put it here. So now I can get the current as, so this is like a single resistance. These two resistance are in series, the external resistance R and the internal resistance of the cell, they are in series. So I can combine this as a single resistance of value R plus R connected to your ideal cell of voltage. So at this point, the potential is E. At this point, if I take this as reference is 0, the drop across this resistance is E and the current flowing is I. So using Ohm's law, I get I into R plus R. Okay. So from this, I get the current I as E divided by current I is E divided by R plus R. So if it's ideal cell means the current will be E divided by R, where the small r is 0. So this current in a real cell, it's slightly less than the ideal cell value. Okay, and this will be not too different if it is a very small internal resistance. So now I'm connecting two cells in series, like I can have two resistors in series and have a single equivalent resistance, right? Similarly, I can connect two cells in series and I can represent, or I can have an equivalent cell, which has got a single EMF, a single internal resistance. Okay, so I have to find the, obviously these two are known cells, so I know the E1 value and its internal resistance R1, and the second cell EMF value is E2, and the corresponding internal resistance is R2. So I'm replacing these two cells by a single cell whose EMF is E equivalent and it have an internal resistance of value R equivalent. So I have to find the relation between E equivalent and E1 and E2, and maybe also R1 and R2, and relation between R equivalent and these known quantities. Okay, so these two circuits are equal in the sense that PA characteristics across the terminals A and C should be same. That's what I want. I say these two are equivalent in terms of these two quantities, PA characteristics across A and C. So for the first cell, I can write VAB. VAB is drop from A to B. B usually stands for drop. So when I write B, so when I write B, VAB, which is drop from A to B. Okay, so that will be this actually is a internal resistance. This R1 is here. I can put it outside to make it clear. Okay, so this is R1, and the current will flow from the positive terminal to the external, whatever is connected. Okay, and then come back here. So direction of current is towards left. This you should know because current will leave the positive terminal, go in the outside, whatever is connected, maybe a resistance, and then we come here. Direction of current is towards left. So going from A to B, there is a drop of P1 okay, because this is high voltage, right? And this is lower voltage. And in the resistance, I'm going against the direction of current. So there will be a voltage rise. So the net drop from A to B is E1, and there is a rise of I into this R value. So the net drop from A to B is E1 minus I1 R1. Actually, I1 is same as I. I will not put I1 because these two cells are in series. Whatever current goes in this first cell, with the same current going here, because they are in series, so I can put the same I for both. Okay, the drop from A to B is E1 minus I1 R1. Okay, similarly, I can put the drop from B to C, the second cell. That will be VBC. So VBC will be E2 minus same current I and a different internal resistance R2. R2 is the internal resistance of the cell, so there is a resistance here. To make it clear, we will draw it outside. And this value is R2. The drop from B to C is this drop. There is a drop here. And the resistance I'm going against the direction of the current flow, so there will be a voltage rise. Voltage rise is the same as a negative drop. The net drop from B to C is this drop minus this rise. That is E2 minus IR2. And the voltage drop from A to C is this voltage drop from A to B plus voltage drop from B to C. This is like common sense. The total drop from B to C, sorry, A to C, I can take it as a drop from A to B plus the drop from B to C. That will be the total drop, right? To get PAC, I just have to add these two. So that will be E1 plus E2 minus I can take commonly outside into R1 plus R2. So this is VA characteristic of the left side, left circuit. This is V of across AC and the current flowing across the points. Okay, so this is the relation VA characteristic of the left circuit. Drop from A to C is the V. I'm referring here, and the current is the current flowing in this direction. Okay, so the same big thing I can get the right circuit. So the drop from A to C is this drop, E equivalent. There will be a drop here. There is a drop here. Okay, and this R equivalent I can put it outside, make it here. So this value is R equivalent. I'm going against the direction of the current is towards left. I'm going against the direction. So there will be rise of I into R equivalent. So PAC, according to the right circuit, it is E1, sorry, it's equal. Equal is the E of the right cell. So it's E equivalent minus the rise, which is I into R equivalent. Okay, that's why I have to prove that. Yeah, R equivalent. Okay, so this is the same VA characteristics. VAC and this is the current. So these two should be the same graph. Okay, so for this to be equal, one way to make this two equations equal is I have to say that if E1 plus E2 equal to E equivalent, and if R1 plus R2 equal to R equivalent, then these two represent the same characteristics. So the right circuit, if we have R equivalent equal to R1 plus R2 and E equivalent equal to E1 plus E2, then the VA characteristics of the right circuit, that is suppose this AC and the current I, and the VA characteristics across AC of the left circuit and the current are same. So we get the important result that when two cells are in series, I can represent by equivalent cell whose EMF is E1 plus E2 and the equivalent internal resistance R1 plus R. Like we have two resistors in series, its equivalent resistance R1 plus R2. That is we studied in 10th standard. Similarly, here for the cells, in addition to the resistance getting added up, internal resistance, we also add up the EMFs of the cell. Okay, so once I know what happens for two cells, I can extend for three cells. If you have three cells, okay, I can replace by a single equivalent cell. The value of the EMF of the first cell is E1, E2, E3, and corresponding internal resistance R1, R2. Every cell will have internal resistance because it's a real cell. So this E equivalent is E1 plus E2 plus E3, and it will have an internal resistance R equal, that will be R1 plus R2 plus R2. Okay, so this I can extend up to n cells. I can have En, and its corresponding internal resistance Rn. So this equal will be so on up to En, so on up to Rn. Okay, so one I can say extension or complication is, suppose I have a second cell whose polarity is reversed. Instead of having this big dash here, I have a short dash here and this long dash here, but other things are same. I mean, normal order. So E1 is like this, E2 is like this. So this is same as having a cell like this, long dash and a short dash, but whose value is minus E2. Okay, so when the polarity is getting reversed, you just have to say E equivalent will be E1 minus E2 plus E3 plus E4 so on to En. But R equivalent will be just addition of resistors, R1 plus R2 plus R2. There is no subtraction of resistors. R equal to sum of resistors, R1 plus R2. There is no minus R2. So, so whatever is getting, suppose E3 polarity is reversed, you just have to put minus E3. Suppose E10 is reversed polarity, you just have to put minus E10. Okay, so n resistors connected in series, we can replace a single equivalent resistance of value, sum of the EMFs and the resistance. Internal resistance, you just have to add them up. Only thing is for equivalent EMF, I have to look up for the polarity of the EMFs. If it is reverse, means I have to put a negative sign here. Okay, so that is the only, you can say, trick or a composition extension of the simple idea. Okay, similarly, once you know how to combine this is cells in series, the next thing is in parallel. Okay, so you have two cells in parallel. Okay, and we have to replace by a single equivalent cell. This is the first cell, E1, internal resistance R1, and second cell E2, internal resistance R2. Okay, so these two cells are in parallel because the voltage drop across, I can say this first cell is connected across the terminals B1, B2. Second cell is also connected across the terminals B1 and B2. The drop across the two cells are same, so they are in parallel. When they are in parallel, any components which are in parallel means the potential drop across its terminals is same. When they are in series means the current that's flowing is same. Here, whatever current is flowing the first cell will come out here, it will enter here. The same thing is here, second cell. Okay, so I have to again get the relation DAC and I, and here DAC and I, and then these two has to be equal, means DA characters has to be equal. So from there we get the relation between equivalent and E1, E2, maybe R1, R2 also, and R equivalent and these known quantities. So in the first circuit, if I do this, in the first branch, obviously the current will need not be same because they are, this can be I1, this can be I2 in general, because they are parallel. No? Only if they are in series, the same current has to flow. Here they are in series, so I'll say whatever current is coming here, the same current that's coming here, coming here, coming here. So they here the current cannot be different. Okay, but here the current can be different because their paths are different. You know, but the drop across the cells is same. Okay. So for the first one, I can write the drop from B1 to B2 in this path, along this path. the voltage drop from, and V1 is same as A. Whatever potential at V1 is same as A. Instead of writing B, V1, V2, I can write PAC. Okay, so the drop from here to here is same as the drop from here to here. Because this part is connecting wire. Connecting wire is ideally it's zero resistance, so there is no drop there. So drop of a AC along this first path is there is a drop here of value V1. Okay, and this internal resistance I can put it outside to make it clear, R1. And in this direction, we are going against the direction of current because assume direction of, or I can say the correct direction of I1 is towards left because the current will leave the positive terminal of the battery or the cell. The direction of current is this one. So moving against the direction of current, the drop, I should say rise. So I have to put a negative sign V1 into R1. Along the second path, the same VAC, I can write as E2 minus the rise in the resistance, internal resistance I2 into R2. So from this, I'll get I1 as E1 minus PAC. I'll write in a short form as P. There is no confusion. Okay. Divided by R1 internal resistance R1. Similarly, I get from this second one I2 as the simple manipulation. You can figure out E2 minus P is actually VAC divided by R2. And if I note what this junction here, this junction, the currents that are flowing in are I1 and I2, and the current that is leaving is I. So whatever current is flowing in should be to have this relation that I equal to I1 plus I2. Okay. So in this equivalent circuit, if I write the same relation VAC, that is drop from, so I'll go along this path, so drop from A to C, this equivalent circuit, that is I'm representing as P, or let me put it VAC only, that is E equivalent minus, because I'm going as base of the current, into I equal, R equal. This R equal distance, is, I can put it outside. Okay, so there is a drop from across the cell, and this resistance I'm going against the direction of current, so there is a rise. So the net drop is drop minus the rise. So this is nothing but B equal to equivalent. I'm representing VAC as V to make it easy. So okay, now yeah. So from this I'll get I as V sorry, equivalent minus V. Equivalent will be on the right side. I'll bring this V towards right. Minus V divided by R equivalent, right? You have the same form. Okay. So now in this relation, okay, I'll put the value of I1, value of I2, and the value of I from this equivalent circuit. Okay. So I, if I put in this circuit itself, this current is same as I1 plus I2, right? So this left circuit, if I do this I equal to I1 plus I2, I just leave this right. Okay, just consider this first circuit. In this, I'll use this relation I equal to I1 plus I2. So I'll get I equal to I1 is E1 minus V by R1, and I2 is the same form, right? Q minus E divided by R2. So this I can do twice as V1 by R1 is Q by R2. Okay. And then minus sign, let me take it outside. It will become 1 by R1 plus 1 by R2 into. This is the original circuit. Okay. So this is the VI relation of that thing. This is the I here, and the V here. Okay. And the equivalent circuit, the VI relation is this one. I don't need this one. Okay, I can stop here. This is the VA relation of the equivalent circuit V and I is here. If I take these two and compare, these two equations or these two VA characteristics should be the same because that's what I want, right? The original circuit equivalent should have the same VA characteristics. This is for the equivalent circuit. This one, this is the VA relation, and for the original circuit, this is the VA relation. So these two should represent the same VA characteristics. So one way to make it same is if equivalent equal to this quantity, if E equivalent equal to E1 by R1 is E2 by R2, should be R2. This one is 2. Someone is chatting. Okay, and suppose these two are equal, and also if R equivalent is same as 1 by R1 plus R2, then these two are same VA characteristic. Is that clear? So this one is VA characteristic of the equivalent circuit, E equal to equivalent minus I into R equivalent. And this VA characteristic of the original circuit, where I equal to something minus something into B. So these two will represent the same equation of that state. E equal to something is wrong here, right? Sorry. So yeah, I have to compare this one, not this one. I made a mistake here. So I have to compare. See, this VA characteristic is I equal to something into B, right? So I have to compare this thing with this one. This is the VA characteristic for the equivalent circuit. This is the same form, right? I equal to right side is some voltage is there and then some V is there. This is that same form. Current is on the left side and V is on the right side. So I have to compare these two. So this I can write as two terms. This is I equivalent by R equivalent minus V by R equivalent. So I should say if this one E1 by R1 plus E2 by R2 equal to this quantity, okay, and also if this E1 by R1 plus 1 by R2 equal to this R equivalent, then these two are same characteristics, VA characteristics. Okay. So here I get the result that R equal 1 by R equal to 1 by R1 plus 1 by R2. Okay. So when two cells are connected in series, this is the result. The equal resistance value is 1 by R1 plus 1 by R2, and E equivalent by R equivalent should be, or I should say E equivalent is related to E1 and E2 like this. Equal by R equivalent equal to E1 by R1 plus E2 by R2. This is same as two resistors connected in parallel. The equivalent resistance should be 1 by R1 plus 1 by R2, right? And the EMS will add as equal by R equal to E1 by R1 plus E2 by R2. Whether you remember this relation is equal to this R equivalent taken to the right side, so it's R equivalent by R1, sorry, R equivalent by R1 into E1 plus R equivalent by R2 into E2. So this is some sort of weightage. In series circuit, it will be just equal to E1 plus E2. But here, E1 is having a weightage of R equivalent by R1 and E2 is having weightage of R equivalent by R2. So that way also can remember this result. So once I have this for two cells in parallel, I can extend it to 10 cells. So you have two cells of value E1 corresponding internal distance R1 and E2 corresponding internal distance R2. I can represent by a single cell where R equivalent is related to R1 and R2 as 1 by R equivalent equal to 1 by R1 plus 1 by R2. So I have to do the calculation, take the reciprocal, I'll get R equivalent. So to get E equivalent, have this relation